Swayam Prabha. Digital India. Educated India.
Let us now try to look at the OpenFlow protocol, which is the southbound interface for the SDN to communicate with the network devices. And this operates between the SDN controller or the network operating system and the switch or the routing devices. And to facilitate this communication, TCP protocol is used to exchange the messages. Often, this can also be encrypted, and we could use any of the TLS variants to facilitate secure communication for the southbound APIs. This basically abstracts all the interfaces that are necessary to communicate from a switch to the controller and vice versa. This means that it has three classes of messages. One, when the controller wants to communicate with the switch, and that's the controller to switch messages. Two, when the switches want to communicate some sort of events or updates back to the controller, and almost these are basically asynchronous event notification types. And three, there will be a query from the controller and a response back from the switch to the controller or vice versa. And these are typically like what are known as the symmetric messages and used for exchange of various information and for diagnostics purposes. And as we speak of OpenFlow, like I said, it started with the Nisira networks in the early 2008, and then the OpenFlow as a standard specifications 1.0 was set up in December 2009. Thereafter, it continued to evolve based on the interaction from the networking community, and a lot more updates started to emerge. And by March 2015, we have the version 1.5.1 of the OpenFlow specification that describes what are the exact messaging constructs for each of these cases, and what is the sequence of operation, in essence the overall protocol for communication between the network operating system or the SDN controller with the OpenFlow devices. Let us look at some of these aspects. For the first of the kind is controller to switch messages, and this is quite essential for a controller to establish the communication with the switch and try to gather the features of the switch in terms of what kind of device it is, what is the OpenFlow version that it is supporting, and how many number of ports, what is the active status of the links that it has, what is the bandwidth. All of these aspects as features of a device, whether it supports secure communication or not, and various other aspects can be queried from the controller to extract the features of the devices. And also there is a configure aspect where the controller can configure the parts of the switch, especially when you want to configure specific ports to be active, inactive, you want to bring down specific links or want to set some VLAN attributes for particular switches. Those can all be done through the configure message. And then you have the modify state operation, which basically is to update the forwarding rules on each of these networking devices. We will look into this in more details. And the packet out is another sense where if a controller wants to send a specific update for the switch to send specific kinds of a packet, it could use this packet out messages. So the other kinds of messages include the switch to controller messages, where the switches would initiate a message, try to reach out to the controller and get the response back and act accordingly. And the most common one that we will see is a packet in message, wherein as the data packets arrive onto the switch, if it is not able to decide what to do with the particular packet, it would query the controller, and controller would run the intelligence that it would to say what should the switch do with this packet, and it will install back the rule with the earlier seen message of either a packet out or a modify state, and then let the switch take particular action on that packet. And likewise, once the rules are installed by the controller, they time out or age out if no more matches happen on the data plane. And once they time out, those rules would be removed from the switch's forwarding table. In such cases, switch would then notify back to the controller saying a particular flow entry that was being set up has been deleted at the switch. And likewise, if the switch sees there is a change in the port status or change in the link flapping when the link goes down or comes back up, the notifications would be sent from the switch all the way to the controller indicating the change in the port status for a particular device on a particular port. And now looking at these, we already start to see that there are a lot more messaging templates that need to be understood. But then we said we wanted to simplify in the beginning for network operators to operate with. But if network operators are now made to learn all of this, this would actually make it a very difficult task for anyone to operate with. So the best part here is that network operators need not have to interact with the OpenFlow or understand the OpenFlow specifications in greater detail, but the network OS or the SDN controller would abstract out all of this and handle it internally. So that way it is a right separation that we can see where the NOS would really fit in trying to abstract out the complexities. And what the network operators in turn use is exactly the high-level abstractions that are facilitated by the network OS. And the table here summarizes the set of kind of messages that we just discussed, and we can, on a broad basis, we can categorize them as per flow basis, wherein the data path entries as the packets arrive, there would be a packet in that would go to the controller from the switch, and then in response the controller would either do a packet out or a flow mod updates onto the switch. And once these kind of rules that have been set by the controller expire, the flow expired rule would be sent out from a switch to the controller. And the others include the configuration kind of messages, wherein for both the switch and a controller can exchange the hello messages to keep their status update and show that they are alive, and what is the information that they can exchange through the feature request. And if controller wants to configure particular aspects, then it would use the set config onto the switch. And likewise, if there is a change in the status of the network topology, some links go up or go down or come up, then port status is communicated back to the controller. This way, the network OS and the switch devices can keep in sync with respect to the status that's going on and enable the network applications to take into account the changes that have happened and modify the characteristics back onto the switch in terms of how the package should be processed. Overall, let's try to put this into perspective and see one of the most fundamental network application, that is the link state routing. So the diagram here is trying to show a topology with 4 switches or the routers S1 to S4 and an application that is written on top of the network OS, that's Digextra link state routing, which is trying to configure and set the routing tables so that all of these routers would do what a link state routing would otherwise do. So we can clearly see now that unlike the typical link state routing where all of the routers have to flood, now there is no need for these routers to flood any of the packets amongst them and try to build the topology information. Instead, they would all need to communicate their status in terms of the port status and the connectivity link informations to the controller. So all the S1, S2, S3, S4 would share their link state information just with the controller, and then the controller would be able to map, build the network graph, and then know what exactly is the topology without the need of any flooding. And once the topology is being built, the application Digextra's link state routing algorithm can be used to update the routing tables to be populated at each of these routers. So let's see how the sequence of operations would happen, considering that we have a base state of link states that are being set, and let's say one of the links S1 to S2 fails. Now, in the traditional approach, whenever there is a failure of the link, again, these routers have to flood the information, what has changed with respect to a link, and then everyone has to collect this update and then reconstruct the routing tables. But here, there is again no such need. what would really happen when the link, let's say S1, S2 goes down is first, as soon as the switch experiences the link down, let's say S1 or S2, it would send a link failure message back to the SDN controller and through the OpenFlow interface. And once this controller gets notified, it would then process this message and update the link state info table indicating that link S1, S2 is now down. And once the link state info has changed, that means the topology or the graph characteristics of the current network has changed. And if we see that on top, there is a Dijkstra's link state routing algorithm that has basically the application that has dependent on this link state information, wherein it would have registered for any changes to be notified back to it, then there would be a notification from the link state change triggered to this Dijkstra's link state routing application. And once the application receives this notification that there is a change in the link state, it would go ahead and try to query the change in the link state and get the current network graph the way it looks. And then it can now centrally compute what would be the routes that would then be functional and what updates that need to be done at each of the S1, S2, S3, S4 if any of them were dependent on the route of S1, S2 link. And then it would pass on this information back to the link state info in the SDN to the SDN controller using the northbound interface. Now, once there is an update that has happened on the link state info from the networking application, this link state routing application, it would then pass on this updates and using the southbound interface down to all the routers S1 to S4, the controller would update the OpenFlow tables or install new rules or delete the rules that are stale or no more applicable and update the data plane features. And once this is done, we would be able to ensure that the routing goes as normal. So having conceptualized how the operations really occur at the level of the application's northbound and southbound interface, let's now try to look more closely into what goes into this southbound interface and what is the means to update specific rules into the switches and routers. And the major construct, like we said, as an abstraction 2 for SDN was to prepare the generalized forwarding scheme, wherein you would prepare the kind of flow tables that would be updated on each of the routers and switches so that the incoming packets would then match on these flow tables and process the packets accordingly to route or forward the packets on to the next hop links. And this is done by the control plane, which dictates what should be the match action entries that need to be set in each of the router's tables using the southbound API. So the main construct here is what we call as a flow table, which is an aggregate of the flow rules that are going to be set on each of the routers, which are then going to be used for matching the incoming packets. So you learned in the earlier class about how the TCAMs operate, and you have the longest prefix match that would happen for all the incoming packets, and the semantics remain the same here. But what is the exact content on which the longest prefix match needs to be done is what gets dictated by the control plane or the network operating system. In essence, the NOS would compute these forwarding tables and then update them on each of the routers in the network. So let's try to look at what each of these updates would look like and what is the notion of a flow table entry. And what we call as a flow is basically a set of header fields that are going to be matched onto the incoming packet. Anything that matches a rule that says what bit fields to be matched on to the incoming data for a particular set of header fields, and if there is a match, we call that a flow. And every entry in a flow table corresponds to a set of flows. And you have a while star that you typically use as a star to say that a single entry can match any of the bits for that particular field, and that way multiple flows can match into a single rule. And this is what gives us more flexibility in defining how you would want to define the forwarding entries. Now you are no more confined to just the destination IP or the destination MAC headers. You could change the patterns of the bits that you want to match on the headers and then take corresponding actions. And you are also not confined to just saying drop or route. You could even modify the packet headers itself. And that's the power of having this generalized match and generalized action pieces. And to disambiguate, if there are multiple matches that can happen and you want to disambiguate the overlapping patterns, we can use the priority bits to say which of the rules, when matched, of the subset of the rules that match, should be picked for processing. And besides, whenever there is a match and you take certain actions, we can also keep specific counters which would enable us to basically track how many bytes or how many packets have been processed by a particular rule and how many packets have passed through a particular port destined towards a particular IP. All these statistics can also be easily attained through this match action pattern. And the core here is defining the router's match plus action rules. In here, we can see if we have to say match and action. As a common thing, we can say you match the source IP with 1.2. I don't care the remaining two tuples. But if the destination happens to be 3.4.5. whatever the last, I would want to drop the packets. And this star is basically a wildcard that would say you can match on any. It doesn't matter whether it is 1.2.1.0 or 1.2.10.255. Any of those would be a match when we say 1.2.star.star. And likewise, we could have a very generic match that any of the IP sources. And if there is a destination that is going to be 3.4.star.star, then I want to forward it. So now the reason I have chosen these two is to say that now any packet that comes with 1.2. Let's say the source is equal to 1.2.3.4 and destination equal to 3.4.5.6. In this case, what you would see is both the rules 1 and 2 would match. But if you see the longest prefix that has matched, that is rule 1. And if you go by the LPM approach, then this packet would be dropped, regardless, even if the packet rule 2 says that you would want to forward, right? So that's how you have the flexibility. And now if you want to override this and say that, no, I want to forward it on a port 2, then you would want to use the priority and say this has a priority 100 while this has a priority 10. And then you can flip to say, okay, I can go by the priority match in this case, besides just the prefix match. And that's how the flexibility comes to the net in terms of managing and configuring the rules. So let's look into how this flow table entries are defined and what are the aspects of a flow table entry in OpenFlow mean. And the first part and the most important one is the rule, which dictates what is it that you would want to match on. And what this says is basically like when a packet comes in, you want to know on which particular port did the packet come for that particular device. And that's called as the ingress port. And when a packet came, what is its layer 2 header look like? The Ethernet source, Ethernet destination, Ethernet type, and including the layer 2.5, like the VLAN ID and VLAN priority bits can also be checked to say whether there is a match on any of these fields. And unlike the switches, which confine just to the layer 2, we can also look at a layer 3 header fields like IP source, IP destination, IP protocol, which is the next header that you would see, and then the IP type of service bits. So at the layer 3, we can match on any of these IP headers. Not just that, unlike the layer 3, routers would just look at these fields. We could also look at the layer 4, that is TCP or UDP source port and destination port at the transport layer. And we could match on any of these fields to now say what specific actions we would want to take. And the list of actions include 1. To forward the packets to a particular port, that is, you receive a packet on one of the links and you want to send the packet on other link. which is basically you receive on port 1, send it out on port 2 or vice versa. Or you would want to encapsulate that packet and forward it back to the controller itself, so that if network operating system or the controller wants to look at the packet and do some processing, we could always send the packets back to the controller. And if we don't know what to do, or if you think there is some malicious packet that you don't want to process, we could as well drop the packet. And if everything seems to be there and the rules are already set, you want to just do the normal packet processing pipeline to say what actions need to be done on that. And typically this is either forward or modify specific fields on that packet header. Like when you think of a NAT, you would want to change if the packet is an outgoing packet, you would want to change from a private IP, private port, to the public IP port details and send the packet out before sending it on to the internet. Or when you receive the packet back, you would want to do the exact inverse. So we can specify all of this using just these flow table entries. So this OpenFlow abstraction of match action helps unify different kinds of devices and helps achieve different kinds of functions in just the commodity hardware. Let's look at how this can be achieved. At first is the switch. And if you think of a switch, what it would do is match on the destination MAC address. And then if it finds an entry in its table, it would forward to one of the outgoing port. And if it doesn't have any match, it would just flood on all the other ports other than the incoming port. And with the match action abstraction, we can specify the rules to say match on the destination MAC address. And then if there is a perfect match, you forward. If there is no match, you flood. And this serves the role of a switch. So we can now implement the switch on a commodity hardware or just on our bare Linux machines. And taking of the routers, which are the layer 3 devices. And what we have seen earlier is that they do the longest prefix match on the destination IP. And once there is a match on the destination IP, they would forward out on a specific link. And now we can specify through this generalized forwarding to match on a particular destination IP. And as the match is found, you can forward it out to route the packet appropriately. And if there is no match, typically the routers would then just send it out on a default port or drop. In this case, now we have a mechanism to even forward such packets to the controller. And when you forward the packets to the controller, it can then find out what is the route that you need to set and then set the corresponding action so that the packet can be forwarded on outgoing link. Thus, we can achieve the functionalities of switch and router using the OpenFlow abstraction. Further up, we can even implement specific middle boxes right within the construct of OpenFlow. Like think of a firewall. What it would typically do is try to match on specific IP addresses, either the source IP or a destination IP, and try to match on the specific TCP or UDP source and destination port numbers. And either it would allow the actions to be permitted, that is, you forward the packets to go and reach the intended destination, or if you would want to block certain packets, then you would drop or basically deny the packets from going forward. So now with the match action aspects, using the action as either forward or drop and specifying the match with respect to the IP addresses and TCP or UDP port numbers as an exact match, we can implement the firewall functionality as well. Also, I mentioned earlier about the NAT. We could do the same, wherein we basically rewrite the IP address and port numbers according to whether the packet is outgoing, then private to public, and whether the packet is incoming, then you can do public to private and then send the packets out. So thus, a simple single abstraction with the match action forwarding mechanism or a generalized forwarding allows us now to implement different networking elements in one go. That is, all the middle box functionalities, the primitive middle boxes, and the routers and switches can be implemented very easily. So let's consider the examples for L2 switching and L3 port forwarding. So the idea is now, like, we want to set up these fields wherein we want to match this particular source MAC, and if there is a match for this, I would want to say that the action that needs to be taken is send it out on port 3. This way, whatever the rule that we match for the source MAC, it says you can send it out on a particular output port. Thus, we will be able to do the L2 forwarding. And likewise, if we have to do the L3 forwarding, that is the router's role, we would match on the IP destination, which can be the longest prefix match or the exact match for a particular IP, and dictate the action to forward it on a specific port. Similarly, the firewall, we can say that, okay, we want to deny any incoming traffic for SSH, and we know the SSH port happens to be 22, then any of the rules, regardless of from what is the MAC ID for what is the destination MAC ID or the IP source or IP destination, we want to block all the SSH incoming traffic. And that way, if the destination port happens to be 22, we just drop the packet. So we have essentially denied any SSH connections for the servers in our network. And likewise, if we want to block a particular source which is seen to be malicious, we can say that we want to match this particular IP, let's say 128.119.1.1, and if this is a malicious IP, we don't want to admit any traffic from that particular IP, then the rest of the fields become immaterial. If there is a match on IP source, we would want to drop any such packets coming from this host. And thus, we could be also very easy to implement the firewall functionality. Now, let us try to see in operation how this OpenFlow works as an example. And what we can see here is that we have a simple topology where we have 3 of the routers and these 6 of the hosts connected to it. And like I discussed before about how we would want to achieve the waypoint routing, or the essence of trying to dictate particular hosts packets would go through a particular switch, regardless of whether that switch, the path is the least cost or not. And if we want to have this control, and let's say we want to send the packets from either of the host 5 or from a host 6, which are intended for either of host 3 or host 4 as destination machines. So from a source here and a destination here in this field, we would want the traffic to go through this particular switch S1. And if this is our intent, what a network operator should be able to say is just that I have these host 6 and host 5. Any flows coming from this has to go to the switch S1. And if we define this rule and then see how it would translate and update would happen in each of the cases, then the network operator can simply push an intent saying any traffic from H5, H6 that is destined towards H3 or H4 should be routed via S1. And how this would reflect back and updates on the OpenFlow rules from the network operating system, let's try to look at this. So if we have such an intent given, then the OpenFlow controller needs to set the corresponding rules on each of the intermediate routers. That's primarily at the S3 and S1 and S2. And at the S3, we would want to see that if the IP source happens to be 10.3. Which is basically matching both the H5 and H6, and if the IP destination happens to be 10.2. That is matching the H3 and H4 on the destination side, then we would want to forward such packets on this port 3, that is this particular link. And that would ensure that S3 would always match these rules and then forward the packets on the leaf output port 3 to make sure that the packet reach the S1. And as the packets arrive at the S1, they would arrive from an ingress port, that is the incoming port, as 1, and the source and destination fields remain the same. Now, our intent is to forward these packets on to the switch S2, that is basically the output port 4. So we would say the action as forward on port 4. And once the packet reach the S2 router, they would reach on an ingress port 2, and then we would want to send the packets back based on the destination IP. That is, if the intent is for host 3, the IP destination happens to be 10.2.0.3, we would want to send out the packets on this port 3. And if it is intended for H4 or 10.0.2.0.4 as IP destination, then we would want to send it out on the port 4 to make sure that the packets reach the corresponding host. And this is how the abstractions and the means to configure specific rules at each of the routers is presented from the OpenFlow point of view to the network operating system or the SDN controller. So I've tried to summarize the essential aspects of how the SDN controller would behave and what is the OpenFlow and how that can be used to set specific rules. But what does it mean to look at an OpenFlow switch if we have to understand in a very broad sense? Now, the key components include for any OpenFlow switch is first the control channel or the OpenFlow channel on which the controller would establish a communication with the corresponding switch device, and any communications would then happen on this channel. And as we said, this channel can be secured using TLS communication. Otherwise, it could be just the bare TCP to ensure that the communication is reliable. And any of the packets that come, the 3 kinds of messages that we discussed, would then update on the data path or make some configurations on these flow tables. And the flow tables are basically a set of tables where different rules are going to be matched based on the given set of rules, and then specific actions are going to be taken. So a flow table consists of many of the flow entries which are going to be matched. And this is what a TCAM would actually be implemented as a TCAM, so that you are able to match all the entries with the wildcards supported. And as the OpenFlow specifications grew, multiple tables were supported. The pipeline of moving the packets from one flow table to the other, taking multiple sets of actions were supported, and also the addition of group tables and meter tables were added so that these common actions could be defined in the meters. Like if you want to do the rate limiting, then you would use a meter table setup, like what is the number of byte counts on which you would want to stop processing specific flows packets. Those updates can be done on the group and meter table. And over the years, like I said, there have been a lot of additions that have happened in this OpenFlow world. We will not have all the time to dig into the details of what all have changed, but this should help us understand and see what all updates that have gone through. And to think of what happens when a packet arrives, it's called the data plane packet processing or the forwarding plane packet processing model. Here, as the packets arrive on any ingress port, that is the incoming port, they would go through first the ingress processing pipeline, which consists of a set of flow tables on which the packets are going to be looked and match in terms of the rules that have been set. And if there is a match, you would want to keep adding what actions you would want to take for that match. And the action itself can be forward to the next table. It's like if I have a match on table 0, I would want to send it out on table 1. And if there is a match on table 1, you would want to send it out on a flow table n, and likewise, and then execute the set of actions. It could also be that you would want to send it to a common group table and process these packets. And once the processing happens in this pattern and you have updated specific things on a common group, you want the packet to be sent out on a particular port, then we have what we call as egress processing or the exit path. Here again you will have a set of flow tables and match actions which are equivalent to what you would see in the ingress, but this is the post-processing on the packet that you would want to do before you send out that packet from the corresponding device onto the output port. And this is how the data plane packet processing model is in the OpenFlow switches. And this OpenFlow facilitates 2 kinds of processing. One is called the OpenFlow only, where this pipeline is strictly defined by the OpenFlow constructs. And the other is a hybrid model that was added in the much later versions of the OpenFlow, where you could also add specific of the switch processing characteristics like L2 Ethernet switching, VLAN isolation, access controls, QoS processing, which may be specific functions or applications that are there within the switch and you would want to exercise. Thus, this constitutes how the packet processing happens within the data plane of the OpenFlow switches. And to look at when a packet comes for a particular device, you can think of it enters a packet on a particular ingress port, and it is going to be first, as the packet enters, you want to extract all the header fields that are relevant for you to match on a particular flow entry in a given table. And once you parse and extract these header fields, you would want to do a match, and if there is a match in any of these flow entries, you would want to apply the corresponding set of actions. And these could be like modify packet or update packet or even drop the packet, as so on. And if there is also a set of actions that you would want to take later, like clear specific actions, like if you want to empty as action set, that can be done through the clear actions as an action type. And once you empty, you would want to do some normal common processing with respect to some specific table. And within each of the tables, as you match, there is also a metadata that can be passed to keep track of what all tables it has tried to match and how it has been processed, and eventually execute all the set of actions that have been accumulated over the set of flow tables, and then eventually send the packet out. And in some cases, you may also want to have a support to clone a packet and send the clone of a packet on a particular egress port. Those kind of actions can also be facilitated now in the newer versions of OpenFlow.